So good morning everyone. We are going to talk about in a multi-part series discussion on ASM. So over a couple of sessions, we'll be talking about Oracle Database 11G Release 2, Automatic Storage Management ASM, and this is the first part of it. I am planning to finish off this ASM discussion in 4 parts instead of putting all of them in one single video, which would be very difficult to manage. To get started off with for ASM, instead of getting into the ASM directly, let's understand what a real life infrastructure demands. I am assuming you are a DBA and your database requires all of these following features at some point in time. The real life infrastructure demands the following features. The first one is the disk fault tolerance. By disk fault tolerance, we mean resilience against a disk failure where no data is lost even if one of the disk fails. So when a disk holding your database data file fails, an outage is evident. So there will be an outage. Either that entire database may experience a downtime, a complete blackout period, because all the files on a particular disk are lost, or it might be a partial outage if you lose non-system related data files, which is other than system, undo and sysocs. If you lose, then probably only that portion of your database will experience an outage while the rest of the database is still up and running. Although backups can be used to get the lost file restored on a fresh disk, it still causes costly downtime. Instead, the disk subsystem should offer resilience against the failure, and the disk failure should be transparent. This is often achieved via RAID, which means redundant array of independent disks. RAID makes the individual disk failures transparent to the application using the data on the disk. So even if one of the disk fails, my application would never see this as a failure. So this is all internally managed within the RAID group, and that's why a disk failure is transparent to the application. Multiple RAID levels can be used depending on what we want to achieve. For example, RAID level 0, which is simply striping of data, it splits the data across all the participating disks in the RAID 0 group. It offers excellent IO performance and scalability, but does not provide fault tolerance. A failure of a single disk in RAID 0 group fails the entire group. All data is eventually lost. RAID 0 offers excellent economy, and by economy I mean cost per storage byte is less. It can be used for non-critical archive data which can be restored from backups, and during the restoration downtime is not a matter of much concern. So in such cases you can opt for RAID level 0 because cost per storage byte is very good. You don't invest in multiple bytes while you actually use half of it, like the way it happens in RAID level 1. If RAID 0 doesn't suffice your requirement because it primarily lacks the fault tolerance, in which case you can opt for RAID level 1, which means disk mirroring. It can be used with two disks which acts as a mirror of each other. Whatever data you store on RAID 1 disk group or RAID 1 group is actually written twice on both the disks in RAID 1 group. So if you lost a disk, the data is still available from the other disk. So if you lose a particular disk from a RAID 1, which is a mirror group, the data is still accessible from the other one. This is normally used for installing the operating systems. It is very expensive, which means cost per storage byte is actually double, and is not feasible for huge data stores. So assume that I want to store a database of 4 TB. I would have invested in actually 8 TB of a data store to get a RAID 1 protection, but it offers an excellent protection. Heavy writes are simply doubled, but one good thing about it is although the writes on both the disks can be parallelized. So if I want to store on a RAID 1 group a file of say 8 GB, the actual write happens is for 16 GB, because both the disks in RAID 1 would receive the same file redundantly. But good thing about it is that both the disks would start writing the file in parallel. So if I start measuring the start of write and the end of write, the start and end of write, the time between is exactly the time it takes to write 8 GB of data. So the takt time, if you see, is not doubled. Although the activity doubles, but since the activity happens in parallel, you don't end up doing a 16 GB of write serially where the time simply doubles. Doesn't happen this way. But if you measure the takt time in RAID level 0, it's actually even better than RAID level 1. So when you store a 8 GB file on a RAID level 0 group, then the data is striped and those stripes are written onto multiple disks. So you get multiple disk cylinders. The probability of getting outer tracks is higher, which also reduces the read write arm movement, which means the IO throughput is the best in RAID level 0. Next is RAID level 5. So we have two problems now. RAID level 0 doesn't offers this fault tolerance, but it offers the best economy factor. RAID level 1 offers you a very good fault tolerance, but the economy factor is not that good. So you need a golden mean, which should be neither that costly, plus it also should offer you some kind of a fault tolerance. Then you can opt for RAID level 5, which indicates data striping with distributed parity. It requires a minimum of 3 disks. Considering the cost and the fault tolerance, it's a golden mean between RAID level 0 and RAID level 1. Along with the data, the RAID controller computes and writes the parity on the participating disks in RAID level 5. This often results in a slow IO performance during writes, because all the disks would be busy all the times. Some of them would receive data, others would receive parity information. So all the disks would be spinning all the time. This is not suitable for data which undergoes frequent modifications, example redulogs and OLTP data. So if you change your data on disk very frequently, then it would result into a very costly write operation. It can be used for archive data which needs to be held on disk and is mostly read only in nature. So if I am talking about archive data which I mostly read and rarely modify, then in such cases you can opt for RAID level 5. But data that undergoes frequent modification, certainly say no to RAID level 5, especially for redo logs. RAID level 10, which is a combination of RAID level 0 plus 1, offers the common benefits of RAID 0 and RAID 1. Oracle recommends for databases RAID 10, or that RAID 10 can also be sometimes expressed as RAID 0 plus 1. The only difference is what you do first and what you do next. Is it that the striping happens first followed by mirroring of those stripes, or is it that the mirroring of a file happens first followed by creating the stripes of those mirrors? So depending on that can be reversed. But Oracle recommends a combination of both, where you get striping plus some kind of a fault tolerance which guarantees maximum availability for your database, uptime for your database, whether you do it as RAID 0 plus 1 or 1 plus 0. Now with the fault tolerance which comes with the investment in RAID controllers, which offers resilience against disk failures. So there is an investment. So if I want this type of a facility, I need to invest in costly RAID controllers, and often more than one in most of the cases. What if one of my RAID controller fails, the other one should take over? So this comes at an extra investment, because RAID controllers control how the data is written onto the disk. RAIDs are rule or algorithm driven. and not content driven. So there's a hard coded rule that whatever file I store on read level 0 has to be striped. Whatever file I store on read level 1 has to be mirrored. It doesn't look into the relative importance of the content that I am storing. For example, assume that you want to store very important data. I believe I gave an example last time on this one. My very important data is the latest Bollywood releases that happened and are available on Pirate Bay. I downloaded them via torrent. Then I have moderately important data, maybe a few songs, MP3 pirated ones, downloaded via some iTunes application or torrent. And then I have very less important data, the Oracle documents that I rarely read. And assume that I have a RAID 1 data store and I want to store all of them on the same disk, then every data gets mirrored. So I don't get an option where I can select that my less important Oracle document should not be mirrored, and my highly important the latest Bollywood releases until I watch them thoroughly and more than once should be redundant, made redundant twice or thrice. There is no such choice. It's not content driven, it's algorithm driven, it's rule driven. So you cannot segregate data which you want to mirror and the data which you don't want to mirror. If anything goes on that disk, everything would be mirrored. ASM allows you to assemble multiple disks into a more cohesive unit called as ASM disk group. An ASM disk group can have disks which are not protected by RAID. So your disk group can be made up of individual disks and those disks themselves are not protected by RAID. An ASM disk group at creation time can select the desired fault tolerance level, and ASM offers you three types of fault tolerance. In case of ASM, we call it as redundancy. So redundancy of your data that goes on a ASM disk group could be any one of the three choices that are normally offered to you by ASM, such as external redundancy, normal redundancy, or high redundancy, offering almost same benefits like RAID but without doing an extra investment in the hardware. You however additionally get control over which files you want to enable fault tolerance or redundancy settings and which you would like to exclude or skip. So even if I create a ASM disk group of some fault tolerance, let's say normal redundancy, which is like RAID level 1, the advantage is I can still cherry pick the files and say these are not that important, I don't want them to be mirrored. And if I don't categorically mark it as an exception, then by default all files will be mirrored. Clear? But there at least I get a content driven choice where I can influence my decisions onto ASM saying exclude mirroring of these files because they are not that critical for me. Consider a real life case of a database that I have created a disk group with normal redundancy. Which is like RAID level 1, quite similar to RAID level 1 if not exactly equal. And then if I store my files, database files onto this ASM disk group, pretty much every file will be mirrored. So whether it's a data file belonging to a system table space, sysocs table space, undo table space, or for that matter even temporary files, or for that matter even files belonging to index table space, all of them would be mirrored. Now if you look at them, temporary files and data files from index table spaces, you don't need mirroring for them. In a worst case, what might happen if one of my temporary file which is there is not made redundant and that the file is lost? In a worst case, you can always add it back because it doesn't hold a business critical data, it only stores intermediate sort results. And the same also applies for index table spaces. Indexes can be recreated on demand. So even if I lose a data file of an index table space, I don't lose much of the data. although only for the period when the index table space is not available, momentarily your performance might suffer. But you can always recreate those indexes back. So fault tolerance is not required for temporary files, and for that matter to the data files, those which are part of your index table space. Now if I would have put this on a RAID level 1, RAID level 1 would have mirrored it anyways. But on an ASM disk group, I can categorically mark these two files as an exception and select a template which would allow me to exclude these files from the normal mirroring style that has been otherwise adopted as a de facto standard for my ASM disk group with normal redundancy, which is not possible in case of RAID. So ASM that way seems to be more intelligent than RAID. There is another disadvantage of RAID, that is if I go for RAID level 1, which is mirroring, I need two disks of same capacity. If I go for a RAID group 1 of two disks of 100 GB each, they would act as a mirror. But consider a case that I went to the market, I said I want one of my disk has failed. I went to the market, I said I need 100 GB disk. The vendor says 100 GB disks are no longer available. They are now the things of past. Nowadays you get the minimum one as 160 GB. So I got that 160 GB disk because 100 GB was not available. I plugged it alongside the 100 GB disk which is still surviving. Now although I made an investment of 160 GB, I cannot use the entire 160 GB. The lower of the two would become the driving disk. So 160 GB disk, another 100 GB disk, put in a RAID group 1, the effective usable size is only 100 GB, which even further adds to my economy factor. The cost per storage byte is still getting higher because of this limitation. However, this is not the case with ASM disk group with normal redundancy. You don't get to see this. You can club disks of varying sizes, put them in a ASM disk group, select the redundancy as normal, and ASM would still not complain about the varying size disk, although this is not recommended. But I am talking about at least the feasibility of doing this under strict cost constraints. This is at least doable in ASM, which is absolutely not possible in case of RAID, although we don't do this in real life, because all our disks in case of ASM would not be actually the physical disk, they would be LUNs, and LUNs are customizable, so you can size the LUN the way you want. But I am still talking about a possibility where you do not have a fancy storage. We are talking about an ASM which purely is built upon the internally attached disks in the server, which is quite possible for a small size or small office, home office kind of an environment. I can still go for an ASM without LUNs, in which case the disk space will come from the internally connected disks in my server, although in real life mostly they would be the LUNs. Next thing I want in real life is the flexibility in handling the storage, meaning at any given point in time you should be able to add, remove, resize the storage disks or locations, whatever you have. Now this is quite difficult. If I use disk as an individual disk, then resizing of a partition is a destructive operation, which means if I have created initially a partition on a 100 GB disk, the size of a partition let's say was 20 GB, and I start consuming the partition, and later I realize this 20 GB is not going to suffice, I need actually a 40 GB partition. You have to drop that partition and recreate another partition of 40 GB, which is a destructive operation. So take a backup of the data, drop that partition, recreate it of 40 GB, copy your data back onto that newly created 40 GB new partition, which is a destructive operation which adds to the downtime. So we do not want this kind of a rigid storage models to be adopted for databases, because data growth to a certain extent can be anticipated, but uh, you cannot be like pundits who can define an exact byte by byte storage requirement every month, every quarter, which is quite difficult to anticipate. Which means uh, there must be a flexibility where if I need more space, I should be able to add additional storage quota. And while adding, it should not ask me to bring down the relevant application. It should be transparent to the application. Similar way, if I think I have allocated more than what I need and it is just a wastage of space if it's lying there, then I should be also able to take back that additional space without disturbing the operations on the data which is stored on that particular storage volume. Similar way, I should be able to resize either on the higher side or shrink on the lower side depending on my storage requirement. So which gives me a flexibility in handling my storage requirement. This is often achieved using volume manager. So most of the operating systems, if you see, they provide their own intrinsic capability of doing volume management. So multiple disks are clubbed together into something called as a volume group, and then from the volume group space is allocated to individual mount points called as logical volumes. Those logical volumes can grow and can shrink on demand without causing any outage to the application which is using the data on those volumes. So in reality, people use volume managers. Most of the operating system nowadays supports volume manager, whether it's Windows, AIX, Linux, HP Unix or whatsoever. They all supports volume management capabilities. Volume management allows you to club multiple independent disks, often called as physical volumes, into a logical container, often called as a volume group. Once you have space in volume group, you can create multiple logical volumes. These logical volumes can then be mounted and consumed. So if I run out of space on a given logical volume, I will procure one PV, which is a disk or a LUN. I will add that PV into a existing VG. The volume group now has enough space, and from the space I can now add more space to a LV. All these operations are transparent and seamless, so they do not ask you for any downtime. Adding, removing a disk is online, seamless and transparent operation, which means it does not require any outage. You can do it on the fly and the application can detect whatever operations you have done automatically. So these features must be offered to you by some operating system. Now volume management capability, if is not an intrinsic feature of your operating system, you need to buy third party software such as Veritas Volume Manager. Now assume that I don't want to use my operating system specific volume management capabilities because it's not that robust, or probably my operating system doesn't have its own volume management capabilities. In such cases, you need to make an additional purchase. For example, you might want to purchase a Veritas volume manager, which means an extra bit of investment in implementing a database. So wherever you don't have the volume management built into your operating system, you may still implement it with some third party volume manager solutions like Veritas volume manager. But remember, the point that I want to convey is I must get flexibility but not at the extra cost. So if it's offered as a built-in feature by your operating system, I am fine with it. But if it comes for an extra cost, that means my implementation of Oracle database is become costlier again. So ASM offers VM like capabilities. So in ASM, you club multiple disks together to create a disk group, and the disk group can have its own fault tolerance level, the redundancy factor. So it offers you RAID plus volume management capability. If I think the disk space available in my ASM disk group is less, I can always augment the storage by adding a couple of more disks to the existing disk group. If I think no, I have allocated more than what I need, I can always take back a disk or more than one disk together from an existing disk group. Now while adding or removing a disk, whatever data is there on your ASM disk group is unchanged, which means again, like a volume management capability, it offers you online, seamless and transparent addition and removal options, plus at no extra cost. In real life, you would expect an improved IO throughput for IO intensive databases. As a thumb rule, one would expect 100 MB of 100 MB per second of IO throughput for every Xeon processor core. So if your system is a multi-core system, multi-CPU, multi-core system, accordingly your IO must also match. The IO speed also must match. Assume that I have opted for, by the way, this rule of a thumb is applicable for IO intensive databases. But if it's a computation intensive, then obviously this rule will not apply. If it's purely scientific computation, then obviously CPU power has nothing to do with the IO pumping capacity of your server, right? So I am assuming that you are doing a general database operation which is IO intensive database. Then to achieve a balance between the computation power of your machine and the IO capability of your machine, as a rule of a thumb, you can lay out something like 100 MB per second for every CPU core. So that means if I have a 2 CPU machine where each CPU has 6 cores, which means my machine would have a total of 12 cores, which means 100 MB, so 1.2 GB per second should be my IO throughput. Otherwise, the CPU will be idle waiting for an IO, and IO is not keeping pace with your computation power. So simply saying that I need more CPUs, probably your database is then doing just scientific application, which is computation oriented, CPU oriented. But if you talk about any other general purpose database, a rule of thumb says that for every one CPU core on a Xeon processor, you should uh, organize at least 100 MB per second of a data throughput. So you need an improved IO throughput. Improved IO throughput can be achieved by using multiple disks, let's say a disk array, which is a collection of several disks, and preferably using the outermost tracks of those disks. Then the latency factor would be less, the seek time would be less, which means an improved IO throughput. So instead of putting my read write actuator arm onto the inner track and reading only with one disk pin a small quantity of data, why not keep that actuator arm on the outer track, let the disk spin still once and read the or rather larger quantity of data in the same time. So use multiple disks, stripe the data so that the data is scattered across multiple disks, and let the data be scattered on the outer tracks of the huge disk store that you have. Then probably that system would give you the best ever throughput. If you think physical disks, the hard drive doesn't offers you the kind of IO that you need, go for some electronic technology like solid state drives, or some caching cards like Fusion IO cards, which offers you higher throughput. Because multiple CPUs with improper IO balance, which means simply it's a dead investment. I'm just giving you an example. By no means this is a marketing campaign. I'm just giving you an example that how IO intensive applications can further make use of some advanced technologies which will improve the IO throughput. Some of them might have an objection. Why only Fusion IO? Why not some other IO? There may be more than one company, but I am accustomed to these type of drives, so that's why I am taking you here. Time timestamp timestamp, which is a in-memory database. Huh. Yes. Now that is correct. Now for example, I am showing you this Fusion IO card. Now this is actually a card which is an electronic system, not like an electromechanical hard drive, which is like a PCI Express card which fits into some of the slot on your motherboard. What I'm amazed with this one is it offers you 10.2 terabyte of a storage in this small card. And what is even more amazing is the IOPS, which is IO's input outputs per second. It offers you 13 lakh IOs per second. And when it comes to doing, this is for read. For writes, it offers you 12 lakh 40,000 IOs per second, which is multi times higher than a disk. Plus, you are not doing any mechanical action, which means you are conserving on the power factor. Your disk is mechanically driven by a motor. The higher the spin rate, the more would be the power consumption, which is not the case within a Fusion IO card. So people, they use disk as a passive storage nowadays, and between the disk and the CPU they add a Fusion IO card with an intelligence module, and then comes the CPU. Now over the period, the intelligence module studies your access pattern. Assume that I have a, say, 100 TB data lying on my disk, but I don't rely on this because disks are very slow. They are electromechanical devices. So people would laugh at some point in time, in the next generation might laugh, saying your days of computing were too pathetic. Your disk used to spin. You would have had that much of a patience where the read write arm places itself on a given track. Then you would wait for one's entire spin to happen just to read X MB of data in one disk cycle. So people would laugh at some point in time because the way people are going impatient. The bandwidth that it offers is 6.7 GB of data transfer per second. So this is excellent for multi CPU systems where there are multiple cores. So people are nowadays getting impatient because processors wise, even if the processor speed is capped at some level, but the number of CPU cores which are independent processing, which offers independent processing cycles, computation cycles, can still consume data. So you need to match from the IO side. If I still use the old disk subsystem, then probably that extra bit of computation power would be lying idle. So that is the case why people add it as a intermediate storage. So I have 100 TB of data on my disk subsystem, which is the slowest one, and in between the disk and the CPU there is a Fusion IO control card which can cache up to 10 TB of data, plus there is an intelligence module. So over a period, the Fusion IO controller will go in a learning mode to find out your access pattern, which is nothing but which are those disk blocks which you require frequently. And once it builds that knowledge, it picks up those disk blocks, put it into the Fusion controller, Fusion IO card. Now the hot blocks, the blocks that you query most frequently, they don't get written to the disk even. Eventually they may be written into the disk, but they are there in memory whenever you need it, which offers you 6.7 GB per second of a data transport between the Fusion IO card and the CPU, which means I am extracting more and more out of my computation power installed in my server, which is basically multiple CPUs where each CPU is having multiple cores. And what I was expecting for a 12 CPU machine, I was just expecting 1.2 GB per second, which you thought is quite high. But the Fusion IO offers at least 6 times higher the speed than what I want. And if that's not 6 times higher, at least I can go for a 72 core machine, which is a very computation intensive environment. So you need improved IO throughput, which can be achieved by using multiple disks or a disk array, and preferably the outer tracks of those disks. Now I am talking about like a old age theory. Now Fusion IO coming in picture, then who cares whether it's internal track or outer tracks, whatsoever, because all the frequently accessed data would be there in the Fusion IO itself. So you need improved IO throughput. Now how does ASM guarantees this? ASM stripes data on all the participating disks in the disk group in case of external redundancy. ASM strips data on all the participating disks in the failure group in case of normal or high redundancy. Since my data is getting striped, I often get more IO bandwidth because now more number of outer tracks will be available as compared to a single disk. Now my data is scattered across all the participating disks, either in case of a disk group, in case of external redundancy, or amongst all the participating disks in a failure group in case of a normal and high redundancy. But in either cases, multiple disks are coming in picture, which offers me improved IO throughput. So the read and the write rate would be better. Avoiding manual intervention in IO in tuning the IO load is also another important factor. Consider that in a system with a classic file system example, the way we use it till date, you keep on adding data to the mounts. Later you experience that some mounts are experiencing high IO while others are experiencing moderate and low IO. Typically we classify those mount points as hot, warm and cold. The hot mount points are those mount points which are experiencing higher disk busy rates. The disk busy rate is high because people are doing more and more IO on those mount points. So the disks are experiencing a more IO storm. In such cases, to subside that particular IO storm, what we do, we move couple of files from the hot disk to a cold disk. The goal is to balance the IO across all the mount points so that you don't get hot, warm and cold. Instead you should get most of the disk in a warm category where all of them experiencing more or less the same IO. But again, few days down the line you would experience that one mount point has become hot, others have become warm and cold. Again migrate those files from the hot disk to the cold disk, which is a manual activity. And whenever you are doing this activity, this often means data would be unavailable for some time. So this is what we do in a database. If my data file to be moved is on a hot disk, you would take the table space or a data file offline, then use a operating system command to move that file from the hot disk to a cold disk, rename it by saying alter database rename file old to new, and then make it online again. Now this means for the moment the data is unavailable, plus a manual intervention is always dangerous. I wanted to move it into drive D, I moved it to drive E, and drive E was anyways the hottest drive, which means again a big risk. Again you have to migrate it back. So a manual intervention always comes with the risk of mental state. That mental state may be fluctuating, which is not good. Now, how does ASM addresses this problem? When you add a new disk to an ASM disk group, ASM automatically triggers IO rebalancing operation. So you would see that, let's say my ASM disk group was having 4 disks as of now, with each disk exhausted to 80% of its storage capacity. Now I added a new disk anticipating that I would need more space. The moment I add the 5th disk into my disk group, data from the existing disk would be automatically relocated to a new disk to a level where all 5 disks then show you the same consumption levels. So the new disk will not be idle. Otherwise, in a classic scenario, a new disk until it receives a file would be in a cold state, while the existing disk would have been in a hot state, because they already hold contents to the 80% of their storage capacity, which means people might eventually do an IO against those files. So whenever this happens in case of an ASM, the new disk will automatically start receiving data. Now IO rebalancing is an online and a seamless operation. So your application, the database doesn't comes to know that whatever data was initially on disk 1 has now been transparently relocated to the new disk that I have added. So which is an excellent feature, which means IO rebalancing to get a more improved IO throughput without manual intervention. The single costliest thing in any IT operation is human. Apart from downtime, it's human beings which is the single costliest thing in any IT infrastructure. Because if he is not mentally prepared or stable, then it can lead to downtime. If the manager gives him a bashing in a closed room discussion, expect a downtime for your database. If my experience and the only DB on the project leaves, the project's progress is jeopardized. So the biggest risk in any process is human being. The most flawless process would be a process which does not involve human brain. Pure mechanics is the most fault tolerant process. Pure mechanics. The moment an human element comes in picture, there is no future for that process. So until databases do their own database management, there are going to be problems. And in an environment where there is only one DB handling the database, the possibility of problem is 100%. And whenever there are two DBAs, the possibility is 200%. The next requirement in a realistic environment would be to get a shared disk with ease of management in cluster environments. A cluster is a collection of computing nodes, servers and computers, and requires the same data to be accessible from any of those nodes necessary memory fusion would be taken care by the software, clustering software, but you still need data to be shared without the added complexity of using raw devices. So when it comes to maintaining the integrity of the data, that one cluster node, if it is modifying the data, the other should not modify the same row piece, will be taken care by necessary memory fusion called as the cache coherence by the software itself, the clustering software. But what about the data that goes on a disk? It still needs to be shared so that each node can still access the desired data at any point in time with whatever agreed protocol they might have used with the given software. Like in case of real application cluster, for a given subset of data that belongs to your database, one node acts as a governor of the resource, master node, while other would request the access to that data from the master node. There might be other ways of governing this. I'm not worried about what software uses what technique of governing the data, which is often called as distributed lock management, DLM, is used by most of the shared file systems. But what I'm concerned about it, how do I make my data presentable to both the nodes? One good technique is to use raw devices. Create a shared raw LUN, map it to server 1, map it to server 2. Whatever goes on that raw disk can then be accessed by both the participating members in the cluster. But raw comes with added complexity, added possibility of frequent accidents. I might reuse a raw device if I don't know that the disk has been used by someone else. Accidents are very common. Plus the complexity. If I fail in planning that how much disk space would be required, how many raw devices would be required, this often would result into added administrative costs. It might lead to disk space wastages, which we want to avoid. So we want something which is very easy as far as the management part is concerned, the disk subsystem, which should be like a file system kind of a storage. People, to address this, they often purchase some cluster file system solution. A general purpose file system is only good to be used inside a single server. What if I want to manage the data on a disk and the disk can experience IO from any node in the cluster, then regular purpose file system is of no use. So you need a cluster file system. Some of the examples depending upon the platform are IBM on AIX offers GPFS. On Linux you can opt for GFS, which is a Red Hat general file system or global file system rather. You can go for Veritas cluster file system, and there are multiple others. In case of Windows environment you can opt for MSMC, which is a Microsoft management cluster, and there are multiple other solutions as well. In case of Oracle also has created in the past its own cluster file system called as Oracle Cluster File System version 2. But then, except for OCFS, all others are add-on purchases. That means if I need it, I need to spend more, making my implementation even a costly implementation. In such cases, you can go for ASM. ASM presents the same disk group to all the nodes in the cluster, and so all the nodes can then extract data from the same shared ASM disk group, which means no additional investment on making cluster file system work in your environment. ASM automatically offers you that. In addition to sharing the ASM disk group, ASM nowadays support via ADVM feature, which is a ASM disk or dynamic volume manager, something called as ASM volumes. So you can create even a logical disk out of a disk group. The space that you have in a disk group, you can create a further logical disk called as an ASM volume. An ASM volume can then be formatted with a regular file system to be used if you want one node mount point, and with ACFS, which is ASM cluster file system, if you want to create a cluster mount point. So from a ASM disk group, you can create a ASM volume. That volume can be then formatted with file system of your choice. You can format that volume, which is nothing but a logical disk, with a general purpose file system, a regular file system on your OS platform, and then once formatted you can mount it on that server. It works like a regular mount point. The only difference is when you store the data, it actually goes to the ASM disk group. If you want to create a clustered shared mount point across machines in a cluster, then you can still create a volume. This time, however, while formatting it, format it with Oracle supplied ASM cluster file system ACFS. Once it is formatted with ACFS, the same mount point can be made visible to more than one machines. That acts as a shared file system in this case. ASM starting with 11G release 2 introduced snapshots of ASM volume, and snapshot is a backup, a read-only point-in-time copy of data. A snapshot is a read-only point-in-time copy of data, but unlike traditional backups, it does not take time, it does not take disk space. A traditional backup involves copying the principal, the file that you want to take a backup of, to some backup location. The time it takes to copy is directly proportional to the data volume being copied, isn't it? So more the higher the data volume, the longer it would take for doing a copy. Also, you end up spending same amount of disk space for backups as principal, isn't it? So if I want to take a backup of a 10 GB file, how long it will take? Whatever time it takes to copy 10 GB. How much disk space it would take? Whatever is the size of my principal. If principal is of 10 GB, I would need 10 GB of a space. Snapshots offer backups in no time and without spending the disk space equal to the size of the principal. So they allow you that the backup which doesn't take time irrespective of the size of the data, plus you don't end up spending the same amount of disk space which is as good as the size of your principal. These are some of the advantages of, or these are some of the desired features in case of a realistic environment, and you see all of them are offered by ASM. So there is no appealing reason why somebody should not be using ASM.